I took some time to describe to you the intuitive origins, so to say, of conformal field theory. It would be, of course, much faster to simply present it in some axiomatic way. And it's done in many books, which you can read. The reason is why I prefer this intuitive way is that I'm actually quite convinced that the existing conformal field theory should be generalizable in some very non-trivial way to higher dimensions. And for that, and we're still lacking some fundamental idea of how to do this. And that's why the way to come up with such an idea would be to analyze carefully the grounds of existing facts. Also about axiomatics, I have some prejudice. I always remember there's a famous phrase by Bertrand Russell who said that axiomatic method, he wrote, axiomatic method has a lot of advantages. However, these are advantages of theft in comparison with honest toil. So indeed, it's get lost. A lot of things get lost when you simply present things axiomatically. Anyway, so our basic formula was the operator product expansion. Symbolically, without details, we can write it down like that. And the fact that the correlation function must be symmetric, must have right symmetries, is expressed. It imposes huge constraints on possible structure constants. By the way, these structure constants are, we can always define them by taking three operators. There's this these terms like x1, 2, delta m plus delta m minus delta l, etc. And they are multiplied by the constant fnml, which actually determines the strength of interaction. And in principle, I put this index on the top. In principle, you can, sometimes it's convenient to introduce the metric by taking two-point function, which again is 1 over x to some power, and you have GMN, which is sometimes it's convenient to introduce, and it is called usually the Zamolodchikov metric. And with this metric you can go, but for us it will be enough to assume that it's flat, and but using it you change the position of indices. Now, the most important part was that in conformal field theory, the matrix elements, or correlation functions of energy momentum tensor are fully determined. We discussed it already. The key point is that we have the word identity, which comes from the general origin of the word identity, as we discussed. I'm simply putting it in a nutshell now. The general word identity is obtained when you make some symmetry transformation, some gauge symmetry transformation. You have some parameter epsilon, the action changes, and you have some fields. It's not, I'm using different letters because it's not restricted to CFT, it's very general. And you have sum over k that's the general word identity. And in quantum electrodynamics, the most that it originally appeared in quantum electrodynamics, and it was related to gauge symmetry when you change fields psi to e to the I epsilon psi. And then you have two terms. One is the current. It's as we already discussed, this is the quantum nether theorem, and so with this symmetry you associate the current. The current is defined in general if you vary the action, and according to nether theorem, you have it should start with epsilon dot, and the quantity which multiplies it is by definition is the charge, is the generator of this transformation, and on the equations of motion we integrate by part, we get two terms. It will be somewhat important to me, so that I'm repeating what you already know. If, let's suppose, we integrate from T1 to T2, we get two terms. One is minus epsilon q dot, and another is complete derivative. Now, if we draw complete derivative, we now say, so it is minus epsilon q dot plus epsilon of T2 q of T2 minus epsilon of T1 q of T1. And there are two ways of proving nether theorem. One is to appeal, just forget the boundary term, appeal to this formula. By the way, how would you explain the following funny thing, that I argued that it must be proportional, variation of the action must be proportional to epsilon dot, because for constant epsilon action must be invariant by our supposition, we assume this. And in a moment I actually integrated by part, and I got epsilon here, not epsilon dot. So it appears that we cannot, something strange goes here. We argue that it must be epsilon dot, and then suddenly we get the term.
It depends on the coordinate.
It depends on whether we assume that we can drop this term only if we assume that epsilon is 0 at the boundary. And that will be important, that's why I'm saying this. So there are two ways of proving things. One is to drop this term. Why should we? And use the equation of motion. The equation of motion tells us that that the action must be stationary, so you get q dot 0. And it's important that we drop this term because equations of motion, action is stationary provided that you don't vary boundary values. And so that's one way of proving this. The other way of proving this is to say that, let's suppose that equations of motion are satisfied, then this term does not appear. what appears as this term. This is the variation of the action when epsilon is not 0 at the boundary. So we require that at epsilon, if epsilon t2, epsilon t1, this variation must be 0 because of the symmetry. So q of t2 must be equal to q of t1. All this elementary stuff is needed because we actually will have two representations for the energy momentum tensor. One corresponding to the first type, the other to the second. They will appear in a moment. What is important is that in energy momentum tensor has only two independent components. The trace is 0, and that's why it is we have the equation in plus-minus notation. We should actually write down the sum over k, 5x1 and that's equal to sum over k 5x1. Here we will have delta k, delta prime of z minus xk. Let me writing it in that way. Let me write it slightly differently. So we have sum over k, delta delta prime of z minus xk plus delta of z minus xk d dxk. This operation, the geometrical meaning of which we will find in a second, is, and it should be applied to 5x1, 5xn. Now, actually the primes here are plus. So it's t plus here, which enters. I remind you our notations, which were that we have, we sometimes use x plus x minus notation, sometimes z and z bar. There, x plus and x minus, roughly speaking, is continuation of z and z bar to the complex domain. It's sometimes, as I said, sometimes convenient to treat them as independent variables. Anyway, this is this can be easily integrated using the formula which in two notations are as I said before, we prove this Euclidean version of the formula is proved by simply defining this thing, and you simply multiply it by some test function and check that you get the delta function here. You can also check it by rewriting it as dz logarithm zz bar is proportional to the delta function, and this is the green function. And here you have 1 over x. You have to define, for the reason I will explain a little later, maybe very soon. You have to define it as a green function. This will be the Feynman prescription for the green function. And so it is principal value 1 over x plus I pi sine x minus delta of x plus. When you integrate it, when you differentiate it, this term gives you the delta function. So that's a very quick reminder. There is nothing deep here, although there is something deep here, and we will turn to this very soon. So we have this operator algebra, and we can determine, we can integrate now this relation, and we get the following identity. What identity for the and that is an important relation, although not yet surprising. We didn't. It's quite rational and clear that you can, when you have traceless energy momentum tensor, then you can reproduce it. You can express it in terms of the correlation function, and this and this are related very simply. When you differentiate it, you get delta prime function from here and delta function from here. You differentiate it from that. Or there's another way of writing this, which is even more. Let's introduce integral dx plus t plus plus epsilon plus epsilon is some function, or integral dz t of z epsilon of z, and call it t epsilon. So let's just take some test transformation. This is a generator of the transformation. This is the transformation which which changes, which makes conformal change of coordinates. And then this formula looks very simple. T epsilon phi of x1 phi of xn. It's simply sum over k phi of x1. It's literally this identity delta epsilon phi of xk phi of xn, where delta epsilon phi is something which we know. It's epsilon of z d phi dz plus delta epsilon prime of z phi. So this is infinitesimal transformation. This is just in the finite form. That would be a transformation phi to df dz to the delta phi of f of z. When f is infinitesimal, you get from this, expanding this guy, you get the first term, expanding, and this comes from expanding this term. So these are basic relations. We are not yet through all of them. That's actually the most important one is still ahead of us, but we will manage, I think, to discuss all important things which are there. Now, by the way, it's you can actually think a little bit in comparison with this Nutter theorem. We have two two ways in usual field theory. We have T mu nu, d mu epsilon nu plus d nu epsilon mu. That's the variation under of some action under generally covariant transformation, and which in our case would be, if we integrate it by part, d minus t plus plus epsilon plus d2. And to obtain this form, which contains a single integral, all you have to do is to take d minus of t plus plus epsilon plus by using the equations of motion, and that reduces to the integral over d z plus epsilon plus t plus plus, and that's precisely this expression. I don't want to go in more detail. I hope you will analyze the logic yourself, and it's precisely the same logic as using using this second term to prove the Netter theorem. We actually have to integrate it out over z minus, and z minus disappears. We get z plus only, and that's sometimes convenient way to do things. But what interests us most is this basic identity, which teaches us, which will help us to decide what is the algebra of the operators. So from now on, we say that the fundamental thing is this operator algebra. You see, at the beginning of this course, I was telling you the basic thing is the Landau free energy. And now I'm saying that this set of data is what is fundamental, namely the structure constants and anomalous dimensions. They are fundamental. They, in a sense, replace the Landau free energy. For the soft modes, what we need when they are interacting, we replace the Landau free energy by this data. To make it clear, how do you think, in what limit, let me ask you this way, in what limit this data can be described as Landau free energy, are equivalent to Landau free energy? What do I need from the theory? Yeah, well, but what I'm saying here is that even at non-trivial critical point, like Ising critical point and others, you cannot use actually Landau free energy in dimension less than 5. But suppose we can. What is then the role of these guys? Huh? Yes, exactly. It's actually Landau free energy is a generating function for this structure constant. First of all, you are completely correct. But we have to add to this that first of all, this free energy makes sense when dimensions are normal. When we have naive dimensions, that defines fields. And vertices in Feynman diagrams, indeed, they are expressed in terms of this. They generate the structure constants. So that's in this sense, this is a far-reaching generalization of the Landau free energy. You cannot describe non-trivial critical point just by taking Landau functional, minimizing it and analyzing it, you have to replace it by this. It's only in the limit of normal dimensions that you can do this. Okay. Now let's take a close look. Before I take a close look, there's one very useful exercise which we gave to you, and I will comment on it a little bit. I told you last time about my unsuccessful attempts to solve quantum electrodynamics using word identity. And the attempts were to look at the Dyson equation, which contains the green function of photon. I'm talking about the ordinary QED. Photon, green function, and this vertex, which satisfies the word identity in momentum space equal to something. In 4 dimensions, this approach doesn't lead anywhere because there are 4 components of gamma and only one relation. You cannot unambiguously express gamma in terms of the green function. If you could, you see, if you could, and we were getting ahead of myself, we will be doing precisely that in 2D. If we could, we simply express it in terms of a green function, and we will obtain a closed integral equation for the green function in quantum law, which somehow sums all Feynman diagrams. Would be quite wonderful, and this indeed happens. You can do this, but in 2 dimensions, and I shall explain why. In 4 dimensions, it doesn't work.
You can do it in QED in 2 dimensions?
Yes, in QED and in a Turing model, basically in many, and in some sense, that's what we're doing here. By the way, if we treat it as a word identity, let's go Let's go to the momentum space. What's the difference between this word identity and the word identity which you would get if you make the Fourier transform? I don't need the detailed Fourier transform, and it will be just more notations, new notations than I need, but there is one crucial difference which you can immediately notice by looking at this between standard word identity here and conformal word identity there. What happens when you take the Fourier transform with respect of z? And so from z we multiply it by e to the iqz, and we have some correlation function which depends on q. What is d? Q. So the difference will be that I will have q minus t plus plus of q and some stuff equal to some green functions. Here I multiply it by q mu, and it's also some stuff, some g functions. What's the principal difference between the two?
Which q's are?
Well, you see, here you can immediately divide by q minus, and you obtain the expression of this energy momentum tensor, in terms of the green function. And that will help us. So since we're dealing not with electric case, it will help us to solve, for example, the quantum gravity problem for this. Now, what would be the analog of this identity in 2 dimensions? Will be something like that. Well, what would be, suppose we have a current, we're now in 2D, and we have a current J plus minus, 2 components of the current. How would you rewrite these word identities? Well, you have...
Q minus J plus.
Yes. The main difference is this second term. If I translate it into gravity, I will get Q minus T plus plus stuff plus Q plus T minus plus stuff is equal to G functions. Okay. Once again, we don't have enough equations in this case. But what is this? Remember, it's a trace which is 0. So the reason why we succeeded is that the trace is 0 because of scale and conformal invariance, and then this term is you can obtain this thing. Now, in quantum electrodynamics, massless quantum electrodynamics in 2 dimensions, and in the theory model, which we suggested as a home exercise, what happens is this. There is the analog of this relation. And the analog comes because if you take in QED, you have the current psi gamma mu psi, and you always have the axial current, which is slightly, well, in normal electrodynamics it would be this thing. And if the masses are 0, then at least classically these currents, both of these currents are conserved. Now, and now comes a crucial point, which I will write formally, but I will explain. Namely, these 2 currents are related. If you take gamma matrices in 2 dimensions, so yeah, which are Pauli matrices, then you have the relation between these matrices, which is just like that. And that means that you have 2 equations, which is the origin of this second current is very easy to understand in 2D. We have the Dirac spinor contains complex field psi plus and complex field psi minus. And as we briefly discussed when talking about the Ising model, although I remind you the Ising model was related to real fermions, not to complex, not to Majorana fermions, not to Dirac fermions. So in this case, you have QED psi plus And you see, remember that psi plus transformed like a square root of coordinates, so it's invariant expression. And what I'm writing is, of course, nothing. You would get precisely the same thing if you take a textbook on field theory, write down gamma matrices, write down the standard Dirac-Lagrangian. I'm just in 2D, it simplifies to this form. Plus field strength square. And from here, you see that you have two independent conserved current, which in our conformal field theory corresponds to what? What are conserved currents which you can form in this Lagrangian? There are two conserved currents, which are nothing but combination of these ones, of course. Nothing, no mysteries here. So, it will be psi plus transformed as a square root of the vector. To get the vector j plus, you simply take a product psi plus, and j minus, psi minus, psi minus. Actually, the vector current will be just the sum of the two, the axial current, the difference of the two. So you see that this time we have enough equations because we have two independent word identities for this current, which is without this field. Actually it's holomorphic and anti-holomorphic, precisely like we have here. Moreover, we will derive the difference between the Tearing model, which we suggested in the exercise, and the quantum electrodynamics is in this term. In the Tearing model, we can replace, it's the same Lagrangian, so this is QED. And you actually, as I stress this, that you can solve it for the reason you can reduce it to a closed integral equation. All Feynman diagrams reduce to this because of these word identities. Let me now, it will be instructive to see how it works in the Tearing model, because it will be directly transformed into conformal field theory. So in the Tearing model, we can write down the equations of motion in this way. D minus psi plus, I'm talking about classical equations now, will be equal to J plus J minus psi plus, and correspondingly for the other thing. Yes. This formula, the interaction Lagrangian in the Tearing model, so this is Tearing. Tearing model is nothing but the four fermion interaction in 2D. Lagrangian of interaction is proportional to psi plus, psi minus, psi minus. We already commented that while this is a well-defined interaction, in the Ising model, where the fermions are real, there are no currents. There is no electric current for real fields. And there is no interaction. So what I did here, I simply varied with respect to psi plus star, and I get this formula. And now we can actually we have to write down the analogous formula for the gravitation, for the CFT case, and in which case it will be something current in some sense will be replaced by the energy momentum tensor. And I actually recommend you to play around in different representations with this Dyson equation, or this is equivalent, of course, to this equation. So try to familiarize yourself with these matters, just keeping in mind where the information comes from. And the information comes from this conservation of two currents. Unfortunately, it doesn't work when you turn the mass on. For the massive case, second current will not conserve, and it's much more it's still solvable model, Tearing model with the mass, but in a much more complicated and awkward way, the so-called beta ansatz, which we may or may not touch in this lecture later. It depends on time. Okay, one more comment, one more general comment, and then we will see how to proceed with this conformal field theory. Let's assume that T++ goes very fast as z goes to infinity. T++, the natural behavior of T++ would be 1 divided by z to the 4th. I shall explain why. And let's see if we can actually reach this. So as we take z to infinity, and you will see why I'm concerned about infinity. You see that the leading term here will come from this, and it will behave like 1 over z multiplies sum over k d dxk applied to this. Now, what can you say about this term? It's zero because of translation invariance. So we see that first thing, if the translation invariance is unbroken, then 1 over z term cancels. So when something cancels, let's expand further and see what happens. It's very instructive, actually. Plus, let's take now 1 over z squared terms. One over z squared terms come from this and from this, and we will get 1 over z squared sum over delta k. And here we have to expand up to the second order. Xk d dxk What can you say about this term?
It also should be zero.
It's zero because
Because
of scale invariance, right? So this is zero, this is zero. Let's go further. This is slightly more complicated, but it is a zero again. Because it's a special conformal transformation, we remember that we saw that special conformal transformations would take sphere to the sphere is just that. It's a infinitesimal version of which finite transformation? If we have infinitesimal transformation of coordinates given by this formula, what is its finite form? This transformation is supposed to, since it's conformal, it will turn sphere into sphere. So which transformation of plane onto plane? It's Möbius transformation. It's the f of z is az plus b, cz plus d. Okay, and this is its infinitesimal version. It's zero again. And now comes an interesting point. Now, finally, we can reach something which contains xk to the cube, ddxk, plus, and so on and so forth, which would correspond to transformations and this time we have to be careful. This time we have to remember that so far we wrote down the following equations. Phi of x1, we exploited, better to say, the following equation. Xn is f prime of x1 So when we said that this is simply infinitesimal version of this equation, you can always go to infinitesimal version, and our conformal correlation functions were invariant under this Möbius transformation. But can we get further than that? And what does that mean? You see, if we try, actually, we gave you a problem when we, in higher dimensions, we tried to take infinitesimal, try to go beyond z square to z to the cube. And that will not be conformal in higher dimensions. In 2 dimensions, it is, of course, conformal. Any analytic function is conformal. But if you try for one moment, if you make a hypothesis that this is true for beyond Möbius transformation, beyond the projective transformation. For example, the simplest term beyond would be z to the cube term, and that's what you will get here. If you assume that this term is 0, the correlation functions will be 0. They had enough. You see, you first you translate them, you dilate them, you conformally transform them. They survived so far. However, that was the last straw. When you go beyond this, they are all 0. It's a good exercise. I have no idea what would be the best way to prove it, but try to prove that if you take z to the cube, there is no non-trivial functions, say 2-point functions or 3-point function, which will survive. But that's kind of simple. But we now have a puzzle. Namely, we have to ask ourselves, what does that mean? The theory, just a few lectures ago, I was saying that in 2 dimensions we have infinite conformal group. Infinite conformal group means that you have infinite number of transformations. Any analytic functions will do. So how to interpret the fact that the correlation functions how to interpret the fact that correlation functions are invariant only under under this projective transformations and not invariant. Also, to help you to find the answer, let's go back to word identities and remember what happened when you take on the right hand side you have transformation of the green function. Remember the structure of the word identities in general, the general structure of word identities in any theory. The structure was you have q minus, or maybe with q plus, q minus t plus plus stuff, and this is equal to the sum of green functions, which were just these green functions. This combination was just transformation of how the green functions transform. For example, if we have the term 1 over z plus, what would be it? What would it? Let me formulate it better. Suppose this is the question I already asked you, we already discussed a few lectures ago. Suppose that in quantum electrodynamics, charge is not conserved. What identity is still there, but when we make gauge transformations of various green functions, we find non-zero result. That happens in superconductors precisely. You have so what identity tells you in this case?
The pole in the correlator in the
Huh?
the pole in this.
Yes, and this is the statement. Indeed, this is the statement that broken symmetry, if gauge symmetry of the vacuum is broken, if the vacuum is not symmetric, leads to massless particle. That's what is called the Goldstone theorem. And we see it immediately from here by just taking q to 0 here, and we get non-zero here, 0 here. Now, when you take q to 0 in coordinate space, what does that mean? You're taking large z. And indeed, this would correspond to what? This would correspond to the pole in Q space. So we are now pretty close. We learned that if you have non-invariance of the green function, then you get a pole which corresponds to Goldstone bosons. And now I want you to explain what's going on. How come, what does that mean that if f is projective, this equation holds? If f is beyond projective, more general, then it breaks down. How to interpret this? The right interpretation is that the vacuum here is invariant under restricted conformal transformation, under projective transformation or Möbius transformation, but the vacuum is not invariant under higher transformations. So we will write down the generators very soon explicitly, which correspond to say z cube term, and these transformations they actually change the vacuum, and they generate Goldstone bosons in this thing. Is for those of you who already have some experience with CFT, the Goldstone boson, and I will be explaining this in a moment, but just those Goldstone bosons are what is called secondary operators. That's important. That's where I'm driving at, but I will explain it now. So important lesson, and I'll tell you why I think it is an important lesson, because we will encounter with similar stuff in any non-perturbative theory of quantum gravity. It's very good example. In quantum gravity, you have general diffeomorphisms, and we will see that. And the vacuum is not invariant under all of them. It cannot be. So there will be the same situation, and in this case, we can explore it completely. In quantum gravity, it's still an open question how it enters into the theory. So let me now proceed and explain this issue with the Goldstone boson. By the way, so far again, I'm probably getting ahead of myself. That may be useful. Suppose what would be the analog of Higgs mechanism in this system, in CFT? You see, I explained what is the analog of Goldstone bosons, but you certainly know that there's a Higgs mechanism also. And what would be its counterpart? And Goldstone boson, I said, is secondary operators, and I will explain what are secondary operators in a moment. So any guess what is the Higgs mechanism? First of all, how to, in the usual, say in the standard model, the Higgs mechanism appears when you add gauge fields and Gaussian bosons disappear and so on. And here, what shall we add to the theory?
You just argued that there are no ghosts.
Huh?
I thought you just argued that there are no ghosts.
Oh, well, no, there is Gaussian theorem, because what I argued was that for the transformation for which this changes, you have a singularity at large distances or at small moment. So there is Gaussian bosons are there, but that's the theory on a regular lattice. It's the Ising model, or some other critical theory in flat space-time. And now I was asking what would be the analog of gauge fields here. Well, I will tell you that the gauge fields will be gravitational fields here, and the Higgs mechanism will, as we will see, will be just eating of all secondary operators by the gravitational field. In the sense of statistical physics, you can visualize this as putting the spin system, the Ising model, onto random lattice, into random. But as I said, we need a few to develop a little bit of apparatus before the. Yes.
But here, there was no ambiguity, because we say this equals to 0 with 1 over z and 1 over z squared, because left hand side.
Yes, you are completely right. But this thing is non-zero.
Yeah, because the left hand side is.
No. Well, the point is that you have. Huh?
Why? All others. Yeah.
Oh, okay. Let me repeat the logic. It's actually important to understand. What I'm saying is that we don't know a priori which symmetries are broken and which are not. We have some vacuum. And we want maximally symmetric. We want to. Actually, that was the. I think I conveyed to you that the whole construction of conformal field theory is based. You just try to make things as symmetric as possible, and then hope, like say scale. You postulate scale invariance with anomalous dimension and so on. So you want to get as large symmetry group as possible without killing the theory. And you find that the vacuum, and that's basically the question if you formulate things in the Hilbert space, which is completely equivalent to this. It's the question whether the vacuum is annihilated by some symmetry generators and not annihilated by the others. And we started looking at this thing, and we found that if we assume that translation invariance is not broken, it's an assumption. If it is broken, we can say, okay, maybe in our theory it is broken. If it's broken, you get a strong singularity here. But let's suppose it's not broken. Then we go, there are still plenty non-trivial correlation functions. We go to the next term, which is a somewhat weaker singularity. We go to the next term, and we still can find non-trivial functions. And so we enhance the symmetry up to the breaking point. That's the philosophy. You see? You assume symmetry, and when your assumption conflicts, you stop when your assumptions conflicts with with a meaningful correlation function. So that's how, and I believe that's the way we should treat quantum gravity as well, but that's much more tricky.
You're trying to describe left object by right, because sometimes people describe it vice versa. So they say how left object scales with z, and then do assumptions.
No, wait a second. No, I don't. I feel something. We don't understand each other. So, what do you explain? What do you mean?
Usually people say that energy momentum tensor has dimension 2, right? So basically, this object on the left scales as 1 with this z4.
Well.
Yeah, but they do it only like in the axiomatic approach.
Yeah, it's you don't know.
But
Yeah.
originally it was discovered in this.
Yeah. Okay. Now, let's analyze a little more this identity. And we see immediately that if we take z to some points xk, I want now to examine what happens when I collide energy momentum tensor with some of those fields. Like here, for example, in the Thirring model, this is a classical equation, which, strictly speaking, will make sense only when you know the operator product expansion. And also another philosophical point, so to say, when I said we have operator algebra, operator product expansions, we have to collide everything with everything and see what will be outcome, whether our algebra is closed. We make a conjecture that our algebra is closed, and we want to find the minimal set of fields on which it is closed. And for that we have to perform all possible collisions, all possible thinkable collisions, and see the consistency condition for this. This is very much like I already mentioned this analogy when you classify semi-simple Lie groups. You introduce certain weights, roots, Cartan generators, and then you commute everything with everything, and minimize and trying to find the minimal set. You see, you can always enlarge. You can enlarge the set of operators, and then you get some mess, some completely uninteresting mess. The wonderful thing is that there is a certain minimal set, both in the cases of Lie algebras and in the cases of conformal field theories. All right. So that's to explain why we must, if we have some operators, we must check whether their collisions with energy momentum tensor gives some other operators. And that, by the way, I'm digressing too much, but we can't stop because there are so many aspects of it, that and all of them may be important in the future. This thing, this operator product expansion replaces the standard canonical quantization. You can actually, when you know operator product expansion, you can easily calculate various commutators and see that they do not coincide with canonical. There is no such thing as canonical quantization, strictly speaking. Although one starts with it just to have something to destroy later. All right. So let's collide these things. We see immediately that if you have t of z phi of 0, the leading term comes from plus, so far we get nothing new. Now we take a less singular term. We get this thing. And now we get the term, so it's 1 over z squared, 1 over z. Now we get the term z to the 0 part, to the 0. And I will introduce a special notation for it, the origin of which you will see in a moment. Let's call this operator, I will call this operator L minus 1. This operator I will call L0. And this operator I will call L minus 2. I will give the general definition in a few minutes. Phi, now this operator L minus 2 phi is defined in the following way. It's defined via its correlation functions with primary operators. And this correlation function, the term z to the 0, will come simply from all terms like that. It will come it will come from delta k z minus xk square plus 1 over z minus xk dtxk. And this should be applied to phi of z, phi of x1, phi of xn. Notice the difference. It looks superficially like a word identity for energy momentum tensor, but it's not, because in energy momentum tensor this field would be absent. But that gives you a precise definition of the coefficient in front of z to the 0 term. Okay, now we can actually proceed like that, and we have a whole bunch of secondary operators. By the way, to compare with this notation, if we look at this thing, let's start with a simple thing. Then what is it? Yeah, sure.
You said that you are going to define L minus 2 phi through this equation. Why you don't define it in terms of a contour integral of correlation function of Tz and f0?
Well, you see, what I'm which class D?
Like a formula from this equation.
Yes.
You can multiply this equation
By some epsilon. Yeah. Sure, I can. But first of all, let me make it very clear. The real definition is just a notation. The definition is that this is the operator which enters with the 0 power of z. That's the fundamental definition. And then we simply use word identity to find what it is. So there's the two-step procedure. We say that when we start expanding, so what we are doing here, let's take, we did I erase? Oh, I erased word identity, which I should never have done. We start with a word identity, and it dictates an interesting thing. It dictates that to us that if you have an anomalous dimension delta, you will also have anomalous dimensions which differ by integers. You see, and this simplest operator, which has dimension delta plus, it has dimension delta plus 2, this operator. So dimension delta plus 2. And we want to find how it is, that's the definition. By the way, when we have this operator, what is the answer for this operator? If I have L minus 1. That's a trivial question. It's simply d dz of phi of z. It's also all secondary operators are defined through their correlation functions in terms of primary operators. And if you have, for example, an operator L minus 1 square, it would be the second derivative here. But there is an interesting difference between L minus 2 and L minus 1, which is that L minus 2 cannot be defined by differentiating with respect to z, itself. You see, when you it must involve all correlation. It feels, so to say, all correlation functions, not only z. While L minus 1 is just simple differentiation. So and L minus 1 square and so on, but there's is defined. We can also this defined L0 phi, and L0 phi again is simply yeah, please.
It's probably a trivial question. How are you going to distinguish L minus 2 phi and L minus 1 squared phi? They should be in the same order.
Oh yes, of course. You have you are completely correct, and there is some point here again z to the 0. And you take L minus 1 square phi. But you already know what L minus 1 square is.
But why? Okay. But how should we show or prove that L minus that we need will have L minus 1 squared, and that L minus 1 square acts as a single?
I'll tell you. To define, well, first of all, I made a wrong statement here. Let me make the right statement. That's a unique definition. To get L minus 1 square, you are right that it will appear dimensionally the same. You have to consider the operator product expansion with 2t. L minus 1 square does not appear in this operator product. It appears in the operator product here. And with that we will do tomorrow. We will see what the general picture is, the general structure of operators. But basically I can say it now already that it will be just L minus 1, L minus nk applied to primary operators, and each one, to answer your question, is defined through the operator product expansion when you have k terms t, 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 and then you start colliding them. That we will do next time. Also, another thing to announce to be done next time is that we will see that these excitations are precisely the Goldstone bosons, which I was talking about. Okay, let's stop here. Yeah, go ahead.
But you would like to finish definition of L naught.
What? Oh, yeah. Okay. So that's kind of trivial. It's simply multiplication by delta.
But will we have something like z multiplied by 0?
Yes, yes. It will come from L naught is the term which contains 1 over z square. So let's look at this. This is L minus 2. Now we have T of z, phi of 0, and so on. So L naught applied. So let's the term which is inversely proportional to that square is just by definition L naught phi. And the only term which is proportional 1 over z square comes from these 2 points. So it will be just the statement that L naught applied to primary field simply multiplies it by delta. When it applies to other fields, it's more complicated. But the general approach is very straightforward. You simply take OPE and you analyze this. This is basically the Laurent expansion in terms of z, and you call L minus n just the Laurent components of the energy momentum tensor. I will clarify and generalize it tomorrow. And what is actually one of the reasons for this problem is that it will contain everything like that. There will be components of current with indices and so on. And it will be simpler than general conformal field theory. So it's an interesting problem. And also anomalous dimensions probably were first discovered in the Ising model, but in the Tearing model, people simply did the following. They said we have a Fermi, the propagator is 1 over p, and that's what canonical quantization tells you. But when you calculate diagrams like that, you get terms like 1 over n factorial. And that creates anomalous dimensions perturbatively. So it's a nice, simple model, and many things to be learned from it. And was learned, actually, from it.
So you said once that canonical quantization is okay with a cutoff theory?
Yeah, yeah.
You don't need a cutoff.
Well, you do need it here. Even in 2 dimensions, if you look at this diagram, you see, I'll tell you why you need it here. You see you have 3 propagators, so that gives you 1 over p hat to the cube. And you had 2 two integrations here, p to the fourth. And it all should be proportional, it should have structure pf of p square. This is, I'm talking about Dyson's self-energy part. It must have this structure for massless theory. And from dimensional analysis, you see that f of p square is dimensionless. And when the dimensional analysis tells you that some integral is dimensionless, don't trust it, because it is logarithm instead. So if you really carefully calculate, you will find the logarithm. And then they will sum up to in the theory model you can do it. And more generally it's complicated. It will sum up to the exponential, so you will have some power of p, provided that p is much smaller than the cutoff. If you take some lattice regularization and go to the distances much smaller, or of the size of the lattice, it all be different, but it's completely uninteresting. Then you can use canonical quantization, but you will not get any result from it.